Alright, so let's talk about concavity a bit. So the definition, right, of concavity is simply this. If you look at the function, right, and if you can draw, and we're talking about with respect to some connected interval, all right? So for any pair of points in some connected interval I, you draw the secant line from, say, point A to point B, right? And if the, say, s of x, the coordinate, the y value of the secant line, as it's compared to f of x, right? If we have that s of x is less than or equal to f of x, right, for all x in the interval from a to b, and if you can do this for every closed interval along the interval I that we're thinking about, then the function would be said to be concave up, all right? Oh, wait a minute. Concave down. I'm an idiot. So you see it's concave down. It's like a upside down bowl, basically. So there, this situation here, if the graph looks like that, if when you draw secant lines from one point to another on the graph, if the secant lines are below the graph, it's said to be concave down. All right. Now, at some point in here, maybe about right here, as you start drawing secant lines, I mean, from here over like this to this, right? If I look at this, say A2 and B2, right? Then if I compare the value of the secant line to the value of the function there, I have what? I have the value of the secant at x is greater than the value of the function, right? For all x in the interval, in this case, in my picture, A2 to B2, right? So if you can do that for all possible secant lines in some connected subset of real numbers in some interval, then you'd say that the function is concave up on that interval, right? So, I don't know, to the limits of my artistry, it looks like this function, if we go from about like here to over here, in here, we have concave down, whereas from, let's see here, it looks like, I don't know, maybe it's hard to judge exactly. It's roughly where B2 is. Something like here to here, it looks like I've got concave up, right? It looks like then I've got a little stretch of concave down again, from about here to here, concave down, and then in here, f is constant, right? That's what I'm trying to draw. And in the constant case, well, you have the secant line is equal to the function, right? So in that case, it's both concave up and concave down. So constant functions are kind of bizarre. They're both increasing and decreasing, and they're both concave up and concave down. Now, different calculus books will thread the needle different ways in terms of that language, but that's the language I choose, so whatever. But, you know, arguing over that kind of thing is kind of like arguing whether or not you've been named correctly. It's just silly. I guess unless your name is, well, anyway, let's not. Don't want to bring Hillary into this. Let's see here. Concavity. Let's see here. Oh, yes. So these, of course, are just, you know, algebraic discussions. Then it turns out, as we study calculus, right, that the second derivative offers its wisdom here. It turns out that we can simply look for concave down. I mean, this is kind of a complicated thing to calculate, right? But on the other hand, if we just have f prime prime of x less than 0 on the whole, you know, for all x in some interval I, then f is concave down on I, and likewise the theorem f prime prime of x is greater than 0 for all x in some interval, then f is concave up on I. So that's, you know, that's pretty nice. So some, you know, standard examples that we should think about. I mean, I'll keep it really simple. Example 1. If I have f of x equals to x squared, right, and I calculate f prime of x, I get 2x. If I calculate f prime prime of x, I get 2. Of course, that's greater than 0. So, sorry, I need to move this up a bit. So, of course, the quadratic f of x equals to x squared, I have what? It's what? It's you know, horrible graph, but anyway, you get the idea. So it's concave up everywhere, right? Another example. If we look at f of x equal to, let's go back to x cubed again, all right? Then f prime of x is 3x squared. As we discussed, it's increasing everywhere. F prime prime of x is equal to 6x. So if you draw the number line or sign chart, if you like, for f prime prime, we have one, number of interest, possible inflection point. By the way, a point where the function changes from concave up to concave down, and the function's continuous, probably should add that in there, then such a point is called a point of inflection. All right. Just because the second derivative is 0 doesn't mean you have to have a point of inflection. That will be our next example. Anyway, so long story short, the sign chart here is minus, 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 plus, 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 and so what we got? This is going to be, I mean, you know, I think you know. So here's the graph, roughly speaking, right? And so it just so happens that the critical point is also an inflection point for this cubic function. Say we're looking at y equals x cubed. It's concave down here, it's concave up over here, right? All right, and example 3. If you look at f of x equals to x to the 4th, it's pretty simple. F prime prime of x is what? It's see, 4x cubed is f prime, so 12x squared, right? So this guy has 0 as a possible point of inflection, but it's not, right? Because the derivative, second derivative bounces there, and it just stays positive to the left or to the right of 0. And of course, that's no mystery because f of x equals x to the 4th is this guy, right? So in fact, f of 0 being 0 is actually a local minimum for that. Of course, this brings us, incidentally, to the second derivative test, which is slightly less useful than the first derivative test because it is silent on a certain case. So here's a little theorem for us, right? If f is continuous near c and f prime of c is equal to 0, and f prime prime of c exists, all right, then 1, if f prime prime of c is less than 0, then f of c is local. Let's see here. Min or max, 2. If f prime prime of c is greater than 0, then f of c is local blank. You fill in the blanks. All right. Well, here's how I fill in the blanks if I forget. I just go back to this example over here, right? And lo and behold, I got so clearly that's a local min. Second derivative is positive, so apparently if it's positive, it's a local minimum. If it's negative, it's a local maximum, right? And the second derivative test, of course, doesn't tell us anything in particular when the second derivative happens to be 0, right? So that's a second derivative test. In particular, to see an example where the second derivative is second derivative test is silent, just look at this, right? Here the first derivative is 0 when x equal to 0, and f prime prime of 0 is 0. So you don't, second derivative test doesn't tell you that that's a local minimum. But of course, if you look at the first derivative test, you get a sign chart which goes from minus to plus. Because if you look at little tangents here, they have negative slope over here, and they've got positive slope over here, and so you change from negative slopes to positive slopes, and so it's a local minimum, right? So first derivative test is slightly more reliable in that regard. There is a higher derivative test, but I'll talk about that when we talk about Taylor's theorem. All right, so that's concavity, that's increase, decrease. Now you use these things together, and you can pretty much graph a function, right? But what I want to talk about actually is a slightly different thing, which is how to bound a function via calculus. So here's a typical question we have. I mean, I have examples of graphing with calculus in the old homework from, if you look in the Calculus 1 notes, I'm going to let you look at my notes and so forth for more examples. I'm just going to focus here on the thing that you probably have thought of less about. So basically, here's the task that we face. All right. Find, say, a little m and a big M, all right, such that little m is less than or equal to f of x is less than or equal to big M, right, for a less than or equal to x less than or equal to b. So if you can do that, these are called bounds, right? These bound f of x on the closed interval a to b. You're like, wait a minute, but are you sure you can even do that? Well, yeah, I am, provided I have a little bit more data. I do need to know, let me show you when I can't do that. So some examples where we would fail. If my function, right, looks something like this. And say that point right there is, oh, I guess I still did it though, didn't I? Oh man. Oh, this isn't the example I wanted. Oh well. So say that point, the hole in the graph is 2 comma. Gee, I guess that looks like about 3. Yeah, sure, 3. I suppose it is true, actually, and I guess, I didn't say I have to find the best choice of little m. So from that graph, I could actually see that I have what? 0. 0 is definitely down here, right? And up here is 3. You can see that between y equals 3 and y equals 0, the graph fits, right? So 0 is less than or equal to f of x is, in fact, I can put strict inequality here. It's less than 3, right? But let's see here. Curses. How to do this? Well, I was thinking about, certainly we get into trouble if we try to do something with a vertical asymptote, right? Like, I feel like I'm not being sufficiently creative at the moment to show you the dangers of bounding things. Certainly something like this is troublesome, right? So here we're looking at y equals to 1 over 1 minus x, I believe. So yeah, something like that would have a vertical asymptote x equals to 1. And if I was so foolish as to try to bound this, say from 0 to 2, right? If I tried to bound this from 0 to 2, it wouldn't go well for me, right? Because it goes to plus infinity that way, it goes to minus infinity that way. You can't find a little m or a big M. You can't bound the function, right? But this much is true. So let me not try to be too extensive on how it can fail. Here's a place where it works anyway. If f is continuous, right? If f is continuous on a closed interval, then there exist little m and big M such that little m less than or equal to f of x less than or equal to big M, and there exists in fact c comma d such that f of c is equal to little m and f of d is equal to big M, where c and d are elements of the closed interval a to b. This theorem that I've just told you here is known as the extreme value theorem, right? It's an important theorem. It's very useful. It generalizes, in fact. As you go on in math, you'll learn that this holds if you replace the closed interval with what's called a compact set. If you have a continuous function on a compact set, you attain your minimum and maximum someplace in that compact set. It's a pretty fantastic result. This is its most basic appearance. Okay, so, and this of course is what guides for, you may remember the closed interval test, right? And the closed interval test is basically how we complete this task, right? So let's look at an example where we bound a function with calculus, all right? So example, my first two examples were non-examples, right? So suppose you have f of x equals to, I don't know, x cubed minus 3x squared plus 1. And I want to bound on, say, minus 1 to 1. All right. So what I'm going to do is I'm going to calculate the derivative. Now I just made this up, so it may not go well for me. I mean, generically speaking, you might need to get a calculator out, do some numerical stuff. So that is, you know, this is calculus. You do have to calculate things, that's true. 3x times x minus, looks to me like 2. Oh man. Well, this went nicely for me. It's almost like I made it up. Okay, but I didn't. So we have critical numbers, x equals to 0 and x equals to 2, right? So so what does the closed interval test tell you? Is this continuous? Well, yes, right? And so what do I have to do? I have to check what's f of minus 1, f of 1, and I also have to check f of 0, and I have to check f of 2. The extreme value theorem tells me, since we're looking at a closed interval and a continuous function, the minimum maximum exists, and then like graphing with calculus tells you, if you think about it, wherever the critical numbers are, that's a place where there could have been a minimum or maximum. We don't even really care to figure out whether it is a minimum or maximum, because there's a finite list of things here, so we can just check them and then pick winners and losers, right? I mean, fine, I could figure it out in like 3 seconds. Look, f prime prime of x is, I mean, I don't need to do this, but 6x minus 6, right? So, for what it's worth, f prime prime of 0 is minus 6, and f prime prime of 2 is 6. So, it looks to me like the 0 is going to be a maximum, local maximum, and the 2 is going to be a local minimum. Anyway, again, this is just for my own amusement. Ignore that. All right, so getting back on track here, the values are what? What we got here? F of minus 1, minus 1, minus 3 times 1 plus 1, minus 3. F of 1 is what? 1, minus 3 is minus 2, minus 2 plus 1 is minus 1. F of 0 is 1. F of 2 is 8 minus 3 times 4 plus 1, right? Is that right? 2. 4 squared, 3. Right, so that's 9 minus, this is like minus 3. Oh. Huh, funny. Oh, but look at this. Should I, I forgot my context. Minus 1 to 1, right? So this one is extraneous. it's not even in the solution set. I often tell students that if I was to be a wrapper, I would be extraneous G. My tagline would be, I'm not even in the solution set. All right. I seem to have got off topic and said unusually stupid things. All right. Okay, so look at these guys. What do you got? 3 choices, this, and this. So it looks like minus 3 is less than or equal to f of x is less than or equal to 1. So there's your bounds. And this is true by the closed interval test, as it's called, which really is just simply built on the back of graphing with calculus and the extreme value theorem. For what it's worth, I can graph. I mean, since we've gotten all this trouble, why don't I just graph it? Again, I don't need to. Stay on task, I wouldn't do this, but it's too late. Let's see here. Y-intercept 1. Interesting numbers are 1, 2, minus 1, minus 2. And so what did I say? F prime prime of 0 is a local maximum rather. F prime prime 2, local minimum. So I guess, and let's see, f of 2 was minus 3. So it's like down here, isn't it? F of 0 is 1, f of minus 1 was minus 3 as well. F of minus 1 is minus 3. So I guess, I keep making irrelevant dots. The graph looks something like f of 2, yeah. Let's see here, oh yeah. Like that. So anyway, the big picture doesn't really concern us too much. The point is, if you focus your attention on the interval minus 1 to 1, which is like this, right? Is 1 a 0? No, 1 is not 0. My graph is slightly askew. Minus 1, right? Basically, this purple and minus 3, I still haven't done it right. Minus 3 is the smallest it is, and the largest value it takes is actually where it has a local maximum at 0, and its value at 0 is 1. So there you go. That's how you can bound a function. Now, sometimes it's not so hard. So for example, if I have f of x equals to, say, x e to the x, right? And suppose I want to bound that on, say, 0 to 2. I probably could do this without calculus, but just to kind of illustrate the method, I'll do it with calculus here. F prime of x is what? It is, e to the x plus x e to the x, which is 1 plus x e to the x, right? And so notice that 1 plus x is greater than or equal to 1 for x greater than or equal to 0. Thus, 1 plus x is greater than 0, right? And e to the x is greater than 0, right? Always. Therefore, f prime of x is greater than 0. Well, I suppose, it's actually greater than or equal to, it's greater than 0 for 0 less than or equal to x less than or equal to 2. In other words, the function's increasing, and so what that tells me is that f of 0 is less than f of x, less than or equal to f of x is less than or equal to f of 2. See, remember what increasing said. It said that if a is less than b, less than b, that implies that f of a is less than or equal to f of b, right? So in this context, I can apply that to the endpoints, and I get, and any middle point, and I get this string of equalities, which says, of course, 0 is less than or equal to x e to the x is less than or equal to 2 e to the 2. And so they're bounds on the function x e to the x between 0 and 2. Now, let's see here. I think let's see here. So I hope that's enough to get us started. We'll use this idea because we'll come to problems later where we need to bound things, and graphing with calculus is a really nice tool set to use to bound things, right? Because if you can figure out it's increasing or decreasing, you can just use the endpoints as bounds if it's increasing or decreasing on the whole set you're interested in. But otherwise, you probably need to use something like the closed interval test, all right? Now, if the function's discontinuous, then, but suppose it's discontinuous, but doesn't have vertical asymptotes, then what you'd have to do would be like break it up on pieces and analyze each piece separately and come up with a bound for the thing collectively. Now, the other way to find bounds, of course, is just by hand-to-hand combat with inequalities, and that's also a method. That's the only method we had to use in Calculus 1 with epsilons and deltas, because that was before we developed the calculus, right? After we have calculus, we can use it to solve problems. But before we had calculus, when we were dealing with epsilon delta type proofs, then we actually had to do hand-to-hand combat with inequalities. And I'll probably do some of that in a later video, but that's kind of certainly less important than these methodologies here, because we do need to be able to find bounds. So, all right, I think that's about all I have to say about graphing with calculus for here. There, of course, is much more to learn, but I'm going to probably go on to talk about, I mean, I suppose I could cover some on optimization and things, but I might do an example or two of that, and then I'm probably going to go ahead and skip over to start working on antiderivatives. Anyway, thanks guys.